we're still talking about PDEs. Okay, that's pretty much where we're going to finish up with the course, is in solving these PDEs. I think you've now been able to recognize these type of equations. That's an elliptic equation. Is it a Laplace or Poisson equation? Poisson. All right. Why? Because we have another term that sets in there. That's a steady state equation. Anybody know why it's steady state?
No change of relation.
Yeah, there's no derivative with respect to time setting in there. Steady state problems, you have to run something that's going to converge. So you keep iterating, or you keep running something until you say the residual is down to a low enough value, I can stop. It's a steady state type of situation. If I want to discretize this equation, these two second derivative terms, you'll notice I'm using a central difference approximation for the derivative with respect to x, central difference approximation with respect to y. Notice what I did right here. Right, I just said whatever the node point is, ij, I'll just set that source or sink term at that particular node that I'm solving for. I am solving for the ij value. So this is the discretized equation set. As I think I indicated last time, those are the remainders. Now what this tells you is that I've got a coefficient setting here with regards to delta x squared and delta y squared. Those are fourth derivative terms. These are terms that tend to act as though they're damping, like artificial diffusion to the equation. So it's attempting to try to smooth out your solution here with this fictitious type of diffusion. Okay, that's what I was just talking about here with regards to truncation. That approximate solution differs from the true solution, as you well know, because of those truncation terms. What you want to do, as you can see, is to reduce the mesh size. So you say, if delta x, remember the truncation was delta x squared. So if I want to try to minimize the effect of that truncation error, what I want to do is shrink down the mesh. Right? So there comes a point where you say, gee, I've got a huge matrix, or I've got a lot of nodes that I'm solving for. Maybe this is good enough. So you have to kind of decide what sort of mesh density you want to take the problem to. When we talk about refining a mesh, it means basically adding more node points. That is, reducing the delta x or the delta y as much as you can. You can always use a higher approximation. Remember that you will need more nodes to differentiate what it is, the derivatives that you're dealing with. That's the difference molecule. When I talk about a central difference molecule, you remember how many nodes are involved? In the molecule in 2D, it would be 5, right? It's always I minus 1, I plus 1, or j minus 1, j plus 1. If you go to a higher derivative, or I mean, not higher derivatives, but higher order, you're going to wind up adding more molecules to this. So you wind up having I minus 2 and I plus 2. And then it gets to the point that this becomes difficult to solve efficiently. Several ways to solve the equation. The two basic methods, explicitly, implicitly. Now I referred to this last time. You remember what I meant by implicitly?
Numbers.
Everything in the computational domain, that is the discretized mesh, or the area that you've set up the mesh, is unknown. Everything is unknown. That's implicit. Explicit, there's only one unknown. Everything else you assume to be known. Circle the definition on these two things. Be sure that you know the difference between explicit and implicit. This will become important when you're solving time derivative problems. You will have a time derivative probably, I think, on the exam next week, but the last homework problem will be a time derivative problem. And I want you to do it one way explicitly and another way implicitly. So you have to do it both. The approach you choose depends on what you're trying to solve, the speed and the storage and so forth. Now, let's talk very briefly about the finite volume method. Here's an ODE. What order is this equation?
Second.
Second order. What's the degree?
1.
All right. So I'm solving a second order ODE here. It's not a partial because I've got D sitting there instead of the partial. If I write this as a simple Taylor series expansion and central differencing, you should be able to immediately grasp that that second derivative is going to look like this. I plus 1, I minus 1, divided by delta x squared. That just comes from Taylor series. There's the first derivative. I plus 1, I minus 1, divided by 2 delta x. That's evaluated at I. That's what the discretized equation looks like. Is there anybody who has trouble doing that? That's called a point discretization. That's using Taylor series. Central difference, it's the one I want to keep drilling into you. That's the most common technique that's used in a finite difference approximation. If I do this as a finite volume, you notice here's this term, here is this term, here is this term. What am I doing? What's the difference? I'm now integrating, and I'm integrating over the cell volume. I now assume that the node point here is defined by a volume that surrounds that node point. Let's see if I can draw it out here for you. So it basically is like this. Here's a node, here's a node, here's a node. This would be I minus 1, I plus 1. I now surround these nodes by control volumes. These go from, if this is I minus 1, this would be I minus 3/2 and I minus 1/2. This would be I plus 1/2. This would be I plus 3/2. You get the idea? If this denotes I minus 1, that's I minus 3/2. That's I minus 1/2. So what I'm doing is balancing what goes into this volume, what goes out. So how am I going to do that? I'm going to integrate. So I'm going to integrate what goes in, what goes out. That's what's going on up here, right here. So I'm going over the central volume, sitting right here. So I'm going from I minus 1/2 to I plus 1/2 of each of those terms. So I integrate it. What happens when I integrate a second derivative? It becomes what?
First derivative.
A first derivative. What does this look like? I minus 1/2, I plus 1/2. This term right here. What does that look like?
Central difference.
No. It's a one-sided approximation, just like you did in the Taylor series. This is the I plus 1/2. That's the I minus 1/2. So if you look, I'm dealing with this, all right? This is the volume that I'm dealing with. So I'm saying, now I'm calculating I plus 1 minus I, and then I minus 1. Evaluated at I minus 1/2 and I plus 1/2. What's going through these faces? So that's that term integrated. Here's the first derivative. What happens when I integrate this? It becomes what? It just becomes phi. And I'm going over that face again, right here and right here. So what am I going to do? Hey, that's easy. I plus 1 plus I divided by 2 minus I plus I minus 1 divided by 2. That's that term right there. What I'm left with is this integral that sits right here. I'm just going to bring this down for right now. This is a big difference between the finite volume and the finite difference. It's how we treat terms like this. This, if you notice, you can collapse this to where it looks what? Exactly like these two terms right here. Right? Exactly like those terms right there. What is this term? How are we going to evaluate this? Okay, I bring this down, I divide through by delta x. So now I've got the delta x squared here and the delta x here. What's this? See this integral? What's this? What method is that? Simpson's rule. So it's a 1/3 Simpson's rule. I'm free to use whatever integral technique I wish with regards to this expression. I can use the 3/8 rule. I can use something else. I can use trapezoidal. I will bring down the 1/3 rule because I know that integration is going to be the same order as what I would get in a central difference approximation had I done this. So this is what's going on. This is what's the process, all right? Yeah.
Could you refresh my memory, please? Is it delta x over 3 times those terms to use the Simpson's 1/3 rule?
Yeah, see, in the Simpson's 1/3 rule, you would have an h sitting there. That h was the same as delta x, so I divided through by delta x.
Right. Okay.
That's why you've got these terms down here. All right? Can everybody do that? Take a good look at that, because I might ask for that maybe on the final. What's the difference between a finite volume and a finite difference? As far as the first and second derivatives, they are exactly the same. The end result is the same thing right here. The big difference is what you do right here. And I suggest probably using the 1/3 Simpson's rule. Be sure you can do this process. Be sure that you understand what we mean here. If you don't, then ask me or come by and see me. This makes a very, very large difference in the way we conserve mass, or that we conserve the values. What goes into this thing must be balanced by what goes out. When you do a point discretization, as in a Taylor series, you don't do anything about conservation. You don't care what's going into something or out of something. That's the major difference. If I want to solve this thing as the Poisson equation, and I set the unknown, the value that I'm looking for is ij. Now, you say, well, what's going on here? Because I have these other terms. Remember, I can set this up in a loop. And so what I'm doing is looping over all the i's and j's. So this is why we call this a recursion equation. So once I set that up, then all I got to do is just do this from 1 to n, or 1 to m, whatever it is, the number of nodes that I have in the x or y direction. And in fact, if this is 2 dimensions, this would be a double do loop. It's a loop within a loop. I'm looping over all the x, I'm looping over all the y. So that's why I've got this thing set up, so I'm solving for ij. Right? So you say, I've got this equal to this stuff on the right-hand side. Now I can solve for phi ij. All right, so the n plus 1 means unknown. Everything else I've done is setting on the right-hand side. The n means that it's known. It's either an initial value that I start with, or if it's the first calculation I've already done. That's called Jacobi iteration. You've seen that before. But now you're seeing it in an application, particularly when you go to 2 dimensions. So it's very simple. The unknown is on the left-hand side, everything else on the right-hand side. Is this very efficient? No. It's slow. You can speed this up by this little trick, which you know as Gauss-Seidel iteration. What's the difference between what you saw in Jacobi versus Gauss-Seidel? See this term sitting right here, the I minus 1 and the j minus 1? You notice it's n plus 1, n plus 1. How do we do that? How can we get away with having 2 unknowns on the right-hand side? It's because we can count on the fact that the computer only remembers what it just did. It just calculated the values in the previous sweep. So you're calculating for the unknown ij at n plus 1, But it already knows what the I minus 1 and J minus 1 is because you've already just done that. So by doing this simple little trick, this speeds up the calculation significantly. That's why you do Gauss-Seidel. And the fact that you've got these setting over here on the right-hand side doesn't bother the computer. It's just going to remember what it just calculated. Otherwise, in the Jacobi, you must go back to the complete previous iteration that you did. So this is automatically updating with the latest or most current value. There's a way to improve this. This is using relaxation. This is over relaxation. Actually, you can do it as under and over. In doing these kinds of problems, these PDEs, you want to do over relaxation. That's called SOR, successive over relaxation. What are you doing? You're doing the Gauss-Seidel that sets right here, but now you have a little omega. You've got a relaxation factor that's setting here, omega and 1 minus omega. This is what you add. That's the only thing. The value of omega varies between 1 and 2. That's over relaxation. You can determine that for any n by m, that is the number of nodes in the x direction, number of nodes in the y direction for any mesh. That's significant. That's one of the techniques that I want you to use for the last homework, SOR. If omega is 1, you get exactly the Gauss-Seidel that you just saw. When that value varies between 0 and 1, you're under-relaxing. About the only time you ever under-relax a solution is when you're calculating pressures in fluids. Otherwise, you want to accelerate this iteration to convergence, and you want to do it as quickly as possible. So that's why you generally tend to use SOR. Rarely do you use SUR. This is how you can find the optimal value for the relaxation factor. That's just an analytical solution for the number of nodes in the x direction, number of nodes in the y direction. This method is quite popular, and it is ideal for doing Poisson and Laplace equations. Direct solution. What do you mean by direct solution? It means that you're going to solve a matrix. That means an implicit technique. So everything's unknown. You got to figure out, okay, if everything's unknown, how am I going to solve for this thing? Matrices. That's how you do it. The one you're most familiar with, Gauss elimination. Elimination methods. You use those for solving a large set of simultaneous equations. Most popular of the implicit methods, alternating direction implicit. Alternating direction implicit. Underline that. That's a very important method. You will see that again and again in future courses. Use a technique to solve these PDEs, ADI. Alternating direction implicit. It uses the Thomas algorithm. That's a tridiagonal. That's the most efficient of the matrix solvers. Why do we call it alternating direction? Because you sweep in the x direction, then you sweep in the y direction. So it alternates back and forth, back and forth. You can do it in 3D. You don't have to just refine it to 2D. In 1D, you don't have an ADI. You just have an implicit solution. So in 2D, it becomes alternating. Same thing in 3D. You just sweep in each direction. The strongly implicit procedure. This is a technique where you don't have to alternate. It's one sweep through the matrix. Actually, that's what I did 35 years ago. I was very young at the time. And published that as far as a way, an alternative to solving versus ADI methods. You go back to the ASME journals, you'll probably see something on solving matrices and PDEs using the strongly implicit procedure. ADI is the easiest, and that's one of the techniques that I want you to use for the last homework. How does it work? You're going to sweep in the x direction, you're going to sweep in the y direction. Let's take a look at this equation. So I take everything that has been discretized in the x direction would involve I plus 1, I, and I minus 1 nodes. Those are setting here. Now I put an asterisk on there because that's an interim or intermediate solution. It still means it's unknown. So the unknown's set on the left-hand side. These are the knowns setting on the right-hand side. Anything that's got an n. So now that's j plus 1, j minus 1. So the sweep in the y direction. We assume those are known. I solve for this implicitly using the Thomas algorithm. I now go down and I say, well, now I've got to pick up the y direction. So now I take everything that's in the y direction, which is j plus 1, j minus 1, and I set that equal to this thing right here, which I've just solved. Right? So those are known. I solve the Thomas algorithm again. So that's the second sweep. Now you notice I've got ij setting right there, and I've got ij setting right there. That comes from the term that sets in the x direction, so we assume it's implicit. That's the term that sets in the y direction, we assume it's known. Same thing down here. So I change the subscript now to n plus 1, because that means that's the second sweep, and that's the final solution that I want. So then I repeat this thing over again and again and again. So it's a two-step process. It's like a predictor-corrector technique. The asterisk denotes unknown or interim. Second step, solve in the y direction. That's the y sweep. You only need to solve q once. You don't want to do it twice. What would happen if you did that? You'd have double the source or sink term going into the solution. So you don't want to do that. You want to put it in one or the other of the equations. Just be sure you don't duplicate it. Thomas algorithm, that's what you use to solve this thing. It's very short code. The algorithm is given in the text. You will need this for the homework. And you can call it in MATLAB for those of you doing MATLAB. Now the SIP, as I said, assumes that all the discretized values are unknown. So you don't have to assume that it's a double sweep, an ADI. So you assume everything's unknown. How many diagonals would that be? I minus 1, j minus 1, the ij, the I plus 1, the j plus 1. So that becomes a 5 diagonal. If you're interested in how to do that, we did that back in '78. You can actually look up the paper to see what the algorithm is for solving. It's much faster than ADI. All right. What's going on is that you're setting up a general equation that's doing this. I have three unknowns. The I plus 1, the I, and the I minus 1 are the unknowns. The A, B's, and C's, and D's, these are just the coefficients. Those are the coefficients that come from the discretization. It could be 1 over delta x squared, or 1 over delta y squared, whatever. Those are the coefficients. D, that's the right-hand side. Anything that's known, you throw over on the right-hand side. So when you look at the Thomas algorithm, you'll probably see it written something like this. So that's what it's solving, is that tridiagonal. Other methods of solving these kinds of equations include cyclic reduction, fast Fourier transforms. Any of you ever do FFTs? You probably haven't been through the double E class. Yeah. Some of you may.
Measurements.
Yeah. Okay, you can actually use fast Fourier transforms if you want to do that. They are the fastest schemes, but they're restricted to the type of mesh and computational domain. If you're interested in using these techniques, which are even faster than what I've showed you as far as ADI or SIP, then the Schwartztraber and Sweet paper that was actually done in '79 is the one that you want to find. And it's got all the algorithms outlined for you. So here's what you'd program. Here's with the recursion statement. So it's fairly easy to set up. Transient terms. Here I have what kind of equation? Elliptic, parabolic, or hyperbolic? We got one of three choices. That's better odds than you get on the strip.
Parabolic.
Who says parabolic? All right. That means the rest of you abstain. You're either elliptic or hyperbolic. You lose. That's a marching solution. right? So it's marching in time. I want to discretize this equation. So here is the d phi dt term. What have I used to discretize the time-dependent term? A forward in time. Like a forward in space would be a one-sided Taylor series approximation in x or y. I can do the same thing for time. So that's a one-sided time-dependent approximation. If I wanted that as a central difference, that would be n plus 1 minus v at n minus 1. But I really don't want to do that. Storage problems. So you want to discretize time-dependent terms, usually as a one-sided time difference. I discretize the del squared operator. So here's the second derivative with respect to x, with respect to y. You've seen those before. Now, it depends on how I want to solve this. Do I want to solve it implicitly, or do I want to solve it explicitly? If I look at this equation, how am I solving it right now? Want to bet your car keys on that?
Not at the moment.
You got one of two choices. You lost. What do you drive?
Piece of shit. Yeah.
N plus 1 is the unknown. Everything else, I assume, would be known. That means it would all set on the right-hand side. It's an explicit one statement.
Do you solve for the steady state values first? And
No,
then-
this is a marching solution in time. So you're marching, you put in a value for delta t, and then you're marching in time over the delta t intervals to some point where maybe it becomes steady state, or maybe it's an oscillatory type of solution. It never converges. So the issue, how do you want to solve the equation? Either explicitly or implicitly. That's why I put those subscripts on there. So numerous ways to do that. The most popular method is called Crank-Nicholson. Underline this, circle this several times. I can tell you right now, it's going to come up either next week or on the final. Define the Crank-Nicholson scheme. It's an implicit technique. That means I'm solving, if I'm using ADI, it's going to be tridiagonal. But there's a nice little trick that allows you to get second order accuracy in time instead of first order, where you saw if we discretize d phi dt and we do a one-sided in time, you know from Taylor series that the order is delta t. Makes sense, right? The Crank-Nicholson allows me to fake that out, and I can get second order accuracy in time. I'll show you how it works. It's pretty simple. That's not it. Well, actually it is, I guess. Let's actually go back here and then I'll show you that table. That's just for your edification. What you're doing is time averaging the terms on the right-hand side. So if I have a second derivative term, I'm going to average that between being implicit and explicit. You go, oh, okay, so I divide delta t by 2, since it's a half step, half in time. So I'm going to add a discretization of, in essence, averaging the unknown values and the known values. Now it turns out it's still tridiagonal, because anything that is known sets on the right-hand side. You understand? So the unknown I would treat as though it were totally implicit, like we've done before. That simple averaging of the discretization in space of the second derivative, or even the first derivative, makes that second order accurate in time. How do you know that? Because if I ask you to do a truncation analysis, you're going to discover, oh, it's second order accurate, because what happens? The first order terms in time cancel out. So that's the most popular method for solving implicit equations using ADI, is the Crank-Nicholson technique. This is a list of various methods that have been around for quite some time. Every once in a while, you may run across one of these things. Even in MATLAB, they may be using one of these things as one of their solution kernels, and you're saying, I wonder how they're doing that. Well, you've got the table. right here of what they've done. Explicit first order. Unknown on the left-hand side, everything else known on the right-hand side. See those little pins? This is the equation. That's a very simple, I don't know why that's equal to 0. That's a very simple equation. Right? This says if it's explicit, as long as that time step is less than 1/2 delta x squared over k, there should be an x right there, delta x squared over k, that's stable. But if that delta t is greater than that amount, what do you think is going to happen to that solution? It's going to diverge. It's saying, hey, wait a minute, this is unstable, I can't deal with this. I blow up. So you get asterisks or all sorts of stuff, or you get an answer back on the PC that you're running on saying, whoop, division by something or other. It just blows up, it just stops. And that's because you violated that time step. You have to remember, in doing anything explicit, you have a time or a constraint on the delta t. We come down here to Crank-Nicholson. Here's Crank-Nicholson. Now remember, here's the term, here's this equation, sitting right here. Unknown there, right? Unknown, unknown, unknown. So it's tridiagonal. What I've done is also add another term. And I've said, okay, we're going to average this between the explicit value, the known value, and the unknown. So it's like taking the explicit, bringing it down here, and also running it implicit. You notice here, this was divided by delta t, or here, the delta t here was sitting right there. But here, we've got, aha, I've divided by 2, right? So I'm averaging. Now these things I won't tell you what they are. They're actually called amplification factors. If you get into advanced methods, it tells you, is this thing going to converge for me, regardless of what I do? Is it going to blow up, and at what point it would blow up, and so forth. Notice what this says right here. Always stable. That means regardless of the size of the time step, it will always give me a solution. Now, if I use a small delta t, I'll probably have a more accurate simulation, just like Taylor series, right? The smaller the delta t or delta x. I use a large delta t, okay, it may not be very accurate in the transient solution, but if I want to be steady state, it'll converge to a steady state pretty quickly. But it says I don't have to worry about trying to figure out what that delta t should be in an explicit scheme. It's always stable. Now these other techniques are pretty well known. They've been around for many, many years. This one by far is the most popular. This one we use on occasion, particularly when we're doing parallel processing, if we're running on multiple processors through the supercomputer. But down here, these are techniques that have been around for many, many years, and you may run into codes that actually use these every once in a while. Notice this one in the leapfrog. What happens? No matter what you do, it's always unstable.
Why would you even have that?
Nuclear engineers tended to do this many years ago, and they couldn't understand why their solutions were always so bad after running for so many hours. And it turned out what they were doing was a leapfrog because they wanted to come up with an accurate delta t, or an accurate transient solution. Well, you see what it's doing? N+1, N-1. So this is a central difference on the time step. So he said, hey, that's second order accurate. This is a piece of cake. We can do this easily. And they would run and run and run for a long time, and then they couldn't understand why it would start to blow up after a while. Well, it turns out no matter what you do, it's always unstable. You can get around this by doing some tweaking, but I put it on here as the list anyway. Just be careful. That's called the Newport-Frankel, and this thing is always, you notice the interesting thing here. It's explicit, but it's always stable. That's still the method I want you to remember. That one. Now, this is a hyperbolic equation. The equation that I showed you previously was a parabolic equation, because that's diffusion. This is an equation where you have what they call advection, right? It has a first derivative. These are called hyperbolic equations. You run into these when you're doing compressible flows, supersonic flows, things of that sort. So here, F just would be UV, and alpha would be delta T over delta V or whatever. Right? The point is that you have a very simple equation with the first derivative. This is a first order explicit. If you try to discretize this doing a forward in time centered in space, right, you notice the j plus 1, j minus 1? No matter what you do, it's always unstable. No matter what you do, you'll never get a stable solution on this. The lax method, it's stable if you wind up keeping the delta t constrained by this. The Levier method, here's another technique. It's stable only if it follows this particular constraint. Two-step lax Windroff. Here's a method that's stable, again with this constraint. Here's a one-step. I won't go into these in detail. Here's a leapfrog. Now, this is interesting. What did we discover on the parabolic equation? Always unstable. What did you discover here for this thing? It's stable over a range. When you're dealing with equations that involve first and second derivatives, like the Navier-Stokes equations for fluids, you're in a dilemma because you've got some parts of it that you can use that technique and other parts where you can't. That's why it's important for you to be able to say, what kind of equation am I solving? Is it parabolic, hyperbolic, or elliptic? And if I'm dealing with a hyperbolic equation, I can get away with a leapfrog. But if it's parabolic or elliptic, you've got to cut it. This won't work. Okay, these are just other techniques and so forth. Be sure you understand the Crank-Nicholson method, and you can apply it. Right? So you're averaging the spatial derivatives between the new and the known or previous values. The nice thing here is that this method gives you second order accuracy in space and time. So when I refer to space, it means delta x and delta y. So they're second order all the way around. That's about as good as you're going to get for as simple as a method as we have. Now, let's look at a simple discretization of a simple advection equation. Here's the equation, d phi dt plus u d phi dx equals 0. I can discretize this. Here's a one-sided difference for d phi dt. See, n plus 1 and n. What have I used over here? Remember what it said. If I do a central difference on the first derivative, it's always unstable. But I can use a one-sided difference here. In fact, this is a backward difference. That's just Taylor series. Right? I'm going from I to I minus 1. Well, I wonder what my truncation error would be. So I just plug in Taylor series into that equation. For each term, I plug in the Taylor series. Here it is. Here's the Taylor series, sitting right there. That's this term. See the n plus 1? There's the n plus 1. There's that value. Here's this value. I don't do a Taylor series on that, but I have to do it on this one. So this would be backward Taylor series. Now I just start canceling out terms. Here's what I'm left with. Here's the original. What I want to do is recover the original equation. But when I truncate things from the Taylor series, what happens? I get excess baggage. That's the truncation terms. Here's the truncation associated with the time derivative term. Here's the truncation that's associated with the spatial, or the delta x term. This is the original equation. What does this remind you of right here? That's a second derivative with respect to x. What does that tell you right off the top of your head? It's like I've added diffusion to this equation. Well, there's no diffusion in that original equation, right? There was no second derivative. Here's the original equation. So look at what I've picked up. I now have a diffusion term. That term wants to damp the solution. So if I have a spike or something that's running through my solution domain, what that term wants to do is to dampen it out or smooth it out. You go, hey, this isn't very accurate, right? How do I get around that? I've got to try to reduce the delta x. Now, what's the order here? Wait a minute. What's the order? This is not so good. This is really going to be crude and somewhat inaccurate. Plus whatever I pick up on this thing. Now, as I get down here, I know, well, second derivative of phi with respect to x. That's the same thing as the original equation setting right here. I can rewrite this second derivative in terms of the original equation so that it turns out to be a first derivative setting right there. So I can kind of go back and substitute in the original equation. So what I wind up with is a minus u squared, the second derivative of phi with respect to x, which, guess what? The diffusion term. So here's what I get. Here's the original equation. Here's the truncation term. So that second derivative with respect to time, I could change into a derivative with respect to x. So now I've got a term that's setting right here, 1 minus u delta t over delta x. Interesting. As long as this term is less than 1, I will have a stable solution. If this term is greater than 1, what do I get? I get a negative diffusion. Welcome to thermodynamics. I wonder why you take a course in thermodynamics. You have now violated the second law of thermodynamics. Entropy. That's what's going on here. You cannot have a negative diffusion. And this technique will remind you immediately that you have just violated the second law of thermodynamics. No negative diffusion. So that says whatever that delta t is, or these terms, that always has to be less than 1. That's the constraint that I have with this particular technique. Actually, I don't want any diffusion at all, but I'm going to suffer with this particular way that I discretize this thing in the Taylor series with that term. That term right there, u delta t over delta x, is called the Courant number. And it says the time step cannot be greater than 1. And that's because of that negative diffusion. All right, there you go. So although you recovered the original equation, you picked up the additional truncation terms. The order of accuracy of that technique, as you saw, is first order. Not really good. There's a particularly interesting method I'll show you that's, if we get time, I'll do it in the last set of lectures where we actually get into finite elements. I thought you ought to be at least introduced to that. This scheme is called the Chapeau function. Anybody know why it's called the Chapeau function? What's Chapeau mean? Hat. All right, many years ago, maybe 30, 35, we were working on one-dimensional finite element methods. And in those days, you couldn't get funding for coming up with something that would involve one-dimensional finite elements. And I was solving it as an ADI sequence instead of the classical finite element schemes that you do now. So coming up with fast solutions with finite elements. So it turned out, we said, wait a minute. In 1D, using linear elements, they look like peaked hats. So let's give it a foreign name. And so we wound up coming up with Chapeau functions. And so the government said, this is really good. Where did you guys come up with this? This is outstanding. Right, we're going to give you funding for Chapeau functions. Well, they didn't realize they were just simple 1D finite elements. And in fact, the numerical, this particular technique is used in the weather forecasting today that you do for your 3 or 4 day forecasts that come from NOAA. They use Chapeau functions. Notice that you've got the unknown setting here, the n plus 1 are unknown values. What have we done? This is like a Crank-Nicholson technique. So I've got I minus 1, I plus 1, I plus 1, I minus 1. So it's tridiagonal, right? Tridiagonal. So I can solve this just like a finite difference. The big difference is how I discretize the time derivative term. And in fact, if you look closely at that, it will almost look like a spline. Not quite, almost like a spline. Anything that's known will ultimately go on the right-hand side. Anything that's unknown will go on the left-hand side, so it's tridiagonal. So in applying the Crank-Nicholson, it turns out that that scheme is second-order accurate in space, fourth-order accurate, second-order accurate in time, fourth-order accurate in space, for the same amount of work that you would do for a Crank-Nicholson technique. That's why places like NOAA and others began using it, because it was the same amount of computational work, but you had 2 orders of accuracy improvement. You get that from the finite element method. And what you do is discretize it instead of an integral technique that you do in the classic finite element scheme. You just stop and form the matrix and fake it out into where it thinks it's a finite difference. All right, now I'm going to give you a homework, but don't go by this one. I'll just leave this one on there. This is the one I gave last year that if you can track down, it might be useful to you. I'm going to have you solve a transient problem, but I'm going to set up different boundary conditions for you. I'm going to add some convection to this thing. But what I want you to do is to solve it implicitly using ADI, and I want you to also do it as SOR. And I want you to compare the 2 techniques, and that way it will make you familiar with using both methods. Now I'll give you this formally next Tuesday, but it'll be based on something very much similar to this. All right, any questions?